Okay, so hello everyone. So today I'll be talking about AI in complex adversarial game. So as introduced in my talk, so actually, how many of you are familiar with alphabet pruning? Can we have a show of hands? Okay, so quite a lot of you. So I think I'll start out with just a bit of refresher on what is alphabet pruning. So and also like the games that I'm talking about. So let me do slideshow. Okay, so the games I'm trying to talk about is first Chinese chess. So okay, like I think many of you are more familiar with like chess. Chinese chess is something quite similar. So you have like a board, then you can move your pieces, and then you can take pieces. And the goal of the game is just to capture the enemy king, which is the two pieces in the middle. If you're not familiar with like what pieces are important, so basically the 6 pieces on your side that you're more interested in are the horse, the rook, and the cannon. Basically, a rule of thumb is if you lose one piece, then likely you get a disadvantage. Okay, another game that I want to introduce is something called ultimate-tictactoe. So ultimate-tictactoe is basically on a board of 9x9, then it's divided to 3x3 boards of 3x3. And your goal of the game is to win the individual 3x3 board that contributes to your bigger board. Then let's say, for example, if your opponent moves somewhere like this, then you can only move within the small square that corresponds to where it is relative to the center. Okay, so those are the 2 games that I will be talking about mainly. So, okay, so to do a search on this kind of game, you might want to have an evaluation function. So evaluation function looks something like this, where let's say if it's a positive value, then it's a situation that's good for red or X, basically the person that goes first. Then if it's 0 means it's quite equal, central. And then if you're losing, then basically you're a negative value. So for example, if you're evaluating a board, and then the board gives you, and then the evaluation function gives you like value of 30,000, for example, that means you have already won the game. But let's say if it's in the middle, let's say 1,000, means you have quite a big advantage, but you're not winning the game yet. So that's the gist of the evaluation function. So the way that you do the search is basically you have something called like the game tree. So game tree is in a node structure. So in one node you have a board, and then the children of the board is basically after you make one move. So for example, you have a Chinese chess board, and then if you move the cannon to center, that's one node, one child node. If you move the horse, then that's another child node. If you move the elephant, then that's another child node. So that's how you can formulate the game programmatically to do the search. So some algorithm, one of the most popular algorithm that you have come across is, of course, is minimax. So minimax is basically you have a max agent and then you have a min agent. So the max agent is basically the agent that tries to maximize the value, and min agent tries to minimize the value. So let's say this is the game tree that you're looking at, right? So these are the leaf nodes that you will try and reach. So you're at the root node now. You're trying to look at which node I should go into. So for that, you pretend that you look into the min nodes and you see what is likely, what is the node that the min agent is gonna likely take. So let's say, for example, on the most leftmost is 8, central is 5, and then the rightmost is 1. And because you're the max agent, you're trying to maximize it, so you're gonna choose the leftmost node, right? So that's minimax. Then the idea of alpha-beta pruning is basically you don't have to search the entire tree. You can cut down unnecessary nodes. So basically the idea is to maintain an alpha-beta window, and then you do pruning when it's alpha is greater than or equal to beta. So let's do an example. So let's say if you're the max agent, you already look at the first child, and then when you come to the second child, you look at number 6, right, the node 6, and then you realize that you don't have to look further. Like, regardless of what is the value at 5 me, is it, even if it's 10 or something, chances are the min agent is just going to choose 6 or another node that's worse than 6. So based on that, you can prune other nodes. And similarly, you can do on to the child on the right. Right, then now we come to the idea of negamax. So negamax is basically just another way of expressing the idea of minimax. So negamax is, instead of having 2 agents, min and max, you just formulate the problem in terms of just one agent. So each agent is a max agent. And what you do with the value is you don't keep the same value from the third. from third perspective, you just use the value, you invert the value. So if you come back to the same tree, then the value of the min nodes in the middle, instead of giving an 8, you invert the value to be -8. Then similarly for the other nodes. So this is exactly the same as minimax, but it's just another way of formulating the search. The reason why we have minimax is because you don't have to split your implementation into a min agent and a max agent. What you do is you will only have one function that represents an agent in general, and you are just the max agent. Right, so that's the idea of alpha-beta pruning. You can combine the max with alpha-beta pruning as well. So, okay, so that's the intro to alpha-beta pruning. So now we come to a few techniques that you can speed up the alpha-beta pruning search. So first is iterative deepening. So iterative deepening, the idea here is instead of doing alpha-beta pruning at depth 5 immediately, for example, what you do is you do alpha-beta pruning at depth 1 first, then depth 2 all the way until depth 5. So the idea of this is that you can use shallower searches to enhance deeper searches. So what do I mean by this? Okay, so let's just have a look at the example just now at alpha-beta pruning. So if you do the search from left to right, you can actually prune 2 branches, right? But that's because you're lucky that you choose to do from left to right. But what if you choose to do from right to left? So if you do from right to left, you can't really prune any branches effectively, right? So the way that you can counter this, like basically, you want to somehow know that you should be able to do from left to right. So how to do that? Basically, what you do is you don't do at depth 2 immediately. You just do the search at depth 1. So at depth 1, okay, so to do the search at depth 1, again, you need some kind of evaluation function. So let's say the evaluation function gives you some value that looks something like this. It doesn't have to be exact, but it's some kind of heuristic to give you how good the node is. So if you do, if you search 0 and then 7, you know that 7 is better than 0, right? So you're going to reorder the nodes to like this. And then now you look at node 10, then you see that 10 is actually better than 0 and 7, so you move 10 to the front. So this is the tree, how the tree looks like when you go into level 2, and then when you search at level 2, you can actually correct the value at the nodes, and then you can prune more effectively. Yeah, so that's the idea, that you can use shallower searches to make sure that you can prune more branches when you go into deeper searches. So let me do a bit of demo of how this exactly works. So I have already written, basically this is my main search routine. So I have a start time, and then I have an end time, and then I'm going to print out the time taken, how much time it takes when I do iterative deepening. So the way that I do iterative deepening is I loop the depth from 1 to max depth, and then for each of that, I just call the search routine with that depth. Right? So if you look at this search routine, it doesn't really make sense because I'm reassigning the move variable to the result of the search, right? So let's just run this to see how much time it takes. Okay, so it's gonna print out searching depth 1, 2, 3, 4, 5. Okay, so it takes around 9,000 milliseconds, which is like 9 seconds, right? So let's say if I don't do iterative deepening, but I do something like, I just do move is equal to this dot root dot search and this dot max depth. Okay, so this is when I don't do iterative deepening, but I just straight away go to the last depth. Okay, so obviously it's not going to print anything. Then it will take a bit more time. Okay, yeah, I think you all can see the significant increase in time, right? Just now I take like 9 seconds. If I don't do depth by depth, but I go directly into depth 5, okay, it's depth 5, then it takes like 20 seconds. So basically with iterative deepening, I managed to cut the search time in half. So Okay, so basically the idea of IDS is that you can reorder the children so that you can cut more, right? Building on that assumption, basically when you search at a deep enough level, you can assume that the first few nodes that you explore are actually the better moves, and the nodes that you explore later are the not so good moves. So based on that assumption, we have something called principal variation search. So principal variation search is, so principal variation search is basically on the assumption that the first move explored is usually the best move, and the rest of the moves are not so good moves. And then what we do is, instead of applying alpha beta window, we apply a no window. Okay, so let's review with how alpha beta pruning works in pseudocode. So we have a negamax combined with alpha beta pruning. So when that equals 0 or when the node is terminal, then we're gonna do some heuristic to give the value of how good the node is. Otherwise, I'm gonna loop over for all the children in all the basically a loop over all the children. Then I'm gonna obtain score is equal to negative negamax of basically the same alpha beta window when at depth -1. And then I'm gonna update the alpha value. So when alpha is greater than or equal to beta, I'm gonna prune and then I return the value of alpha. So that's negamax with alpha beta pruning. With principal variation search, it looks something like this. So the part in blue is changed to this. Okay, so let me just dissect what exactly is happening here. So of course, if you're at first move, then nothing special. You're gonna do the same principal variation search on the children as per normal with the same alpha beta window. But then if you're not in the first move, what you do is you do with a null window. Instead of negative beta, your upper bound is actually negative alpha -1. So what this does is actually it fails the children faster. So yeah, it does make sense that with a smaller alpha beta window that you can fail faster, right? And then of course it's not guaranteed that your first move is always the best move, right? So if score is greater than alpha, that's when you know that from this no window search, then you discover that actually another move is better. Then this is in the case that it actually happens. And then this is the condition in the case that you're already in the null search. You don't need to redo the null search, right? So in case that you're not in the null search, basically the width of the alpha beta window is greater than 1, then you're gonna do a full search. Right. So the full search again is just the same PV search call on the children. Right. So essentially, okay, so let me just do a demo of how principal variation search. So okay, let me remove this. Okay, so just remember just now when I did the full thing without any modification, I did it in around 9 seconds at depth 5. So if I go into our main search routine, so okay, I look over all the children, and then this is the PV search part. Right, so instead of doing this entire PV search, what I'm gonna do is I'm just gonna call the full search. Okay, and then instead of this being non-PV, it's actually PV. Okay, so let's try out how much time it takes when I'm not doing PV search, but just normal negamax. Okay, I think it is probably gonna take more than 9 seconds. Okay, let me continue the presentation while this demo is running. Okay, so so in Chinese chess, we have something called the move labels. So okay, when you have not come to these few techniques, you don't differentiate between different moves, but actually there are some moves that you need to take care of. So basically there's a capture. Capture is basically when the move results in your opponent's pieces being captured. Check is when your move results in your opponent's king being checked. and quiet move is basically nothing is happening. So those are the few labels. When you read Stockfish code, maybe there are more labels than that. But sometimes one move can have multiple labels. So sometimes the move can be both a capture and a check, for example. Okay, so let me, okay, still haven't finished, but I get, yeah, y'all get the idea that actually it takes much more time when you don't do PV search. Okay, so let me just stop the program. Okay, so, okay, with this move label, let me move on to the next technique called quiescent search. Okay, so in quiescent search, okay, so remember this is the code that we have derived so far from principal variation search. And when depth is equal to 0 or when no is terminal, previously what we do is we just do a heuristic evaluation. But when you do something like Xiangqi or like normal chess, what you do is you don't just evaluate the heuristic, you also do something called quiescent search. So what exactly is quiescent search? So let me demonstrate to you what is the problem if we just stop the search but we don't continue. Okay, so let's say this is the Alright, give me a second. Okay, so let's say this is the configuration of your board, right? So your red, and then okay, let's just assume that you just look at depth 1. So what is the best move in this case? So we just look at all the moves at depth 1, right? So if you take a look, maybe there's this move, or there is this move, or like even the best move is here, right? Okay, why is it the best move? Because I just capture a piece, right? When I capture the piece, then opponent basically lose one piece, and then I basically gain a piece, right? So that's obviously good for me, right? Okay, another example is this. Okay, the string is not exactly working, so let me do manually. Okay, so let's just have a simple game like this, right? So again, I'm just looking at depth 1. So red, right, has like some option, like maybe move the king, or maybe red can move the king here, or like red can move the car. But the best move in this case, if I just look at depth 1, is this, right? Because you're taking the opponent's horse, and then so you're basically gaining a piece, right? Okay, but I mean at this point, I think you all see that I'm not making sense. Why? Because if you don't look forward further, then you don't see that actually black can capture back the piece. So this is something called the horizon effect. What it does is basically you're looking at a certain depth, but you don't look further, then you're basically blind to certain things. So then your evaluation function, you can't expect it to work properly for all the boards, right? Like if let's say your evaluation function is like how many pieces are left on the board, then obviously this board is going to give you like a very good score, but actually if you look just one step further, you can see that there's a capture move. So to counter this, what we do is we don't stop the search, but we do something called quiescent search. So what quiescent search does is okay, so instead of searching the full tree, so let's say this is the tree that you need to search, right? You don't search the full tree, you only search the capture moves, right? So if it's a quiet move, then you don't necessarily have to look forward. But if it's like a capture move, then you need to explore further to see whether there's any capture that decrease your score. So, but this search doesn't necessarily give you the best value, right? So let's look at how quiescent search look like in pseudocode. So again, let's just recall this is negamax, right? So so for quiescent search, this is the difference. You have these few extra lines. So let's just dissect what exactly is happening. So because remember, we don't search the full tree, what we do is we need some kind of heuristic. We still need to evaluate it in case that, let's say, if you search just the capture moves and your value decrease, then you're going to return the heuristic value instead. Right, that's the first thing. And then the second thing is when looking through the children, you only look at capture moves. You don't look at any other moves. Okay, like in some variations of quiescent search, you may look at check moves as well. That's really dependent on your choice. But yeah, the capture moves is a must to look through. Otherwise, yeah, so that's Poisson search. Okay, so let me move on to the next technique. So something called late move reduction. So if we assume, previously you can assume that the first few moves are the best move, right? Especially the first move. Then what we can assume is the moves that are explored later are usually the worst moves. So what we do is we don't exactly have to look through those moves that deep, right? Like when you think about chess, right, you think only of the first few very good moves, but you don't have to look at the bad moves, right? Then the bad moves, you probably just take a look at like one or two moves that you already know that it's not a good move. So this, okay, but the late move reduction, what it does is gonna just reduce the depth for no search. So let's look at how the tree is like. So let's say if this is your tree that you need to look for, if you need to search for, this is the tree that you need to search, right? Then late move reduction is basically you reduce the depth for the last few moves. Okay, so in terms of pseudocode, this is, okay, so again, this is the PV search. And then, so this is the main search, this is the main call to the child, right? Then, okay, instead of simply call to the child, what you do is you're gonna determine what's the depth that you need to, what's the depth you need to do. So for example, if index, basically the index of the child defined over here in the loop, if the child, let's say index is greater than 3, then you don't need to look at the new depth can be depth minus 2, for example. This is pretty much depend on how you want to manual to, maybe it's depth minus 3. In Stockfish, I believe it should be depth minus 7, something like that. So, and then when you call the no move, instead of calling depth minus 1, you call this new depth, dependent on the late move reduction. So let me do a bit of demo of how this works. Okay, so let me just uncomment these changes. Okay, so late move reduction is right here. So I think it should look familiar, right? So this is new depth, and then I'm going to use this new depth in the no move window. Okay, so I'm going to comment this out and see how much time it takes. Okay, it takes like 14 seconds. So again, by using late move reduction, I managed to reduce it to from 14 seconds, 15 seconds to 9 seconds. So yeah, that's basically because at the late moves, I don't exactly have to look through the same depth. I can look at the shallow depth and just to verify that it's actually a bad move. Okay, so let me uncomment that. Okay, so now that with that, we come to the next very important technique called transposition table. So transposition table is not, it doesn't work by itself, but it combines very well with some other techniques. So transposition table is basically the idea that you can save your search results for later searches. So what you store in transposition table usually is the state, which state are you at, what is the bound type. So the bound type is basically if you do sometimes the result is not exact. Sometimes the result is you encounter a beta cutoff or an alpha cutoff. So that's the so-called bound type. And the depth, basically what depth did you search at when you encounter that same table, and the score that you arrive at. So this search usually can be combined. It doesn't work by itself again, but it combines with some other techniques. So one example technique that it works with is called futility pruning. So futility pruning is you discard nodes that have no potential to raise alpha. So okay, so let me go through the pseudocode of how exactly futility pruning. So this is before you go into the loop, right? So after this, there's going to be loop. But what you do is you first do some transposition table cutoff. The logic for the cutoff is a bit complicated, so I decided to omit that. But with futility pruning, what you do is you do some static evaluation. This evaluation isn't exactly the heuristic, but it's a combination of heuristic and the transposition table value. And then, okay, so what are the conditions for you to do futility pruning? So first off is you do you only do it on non-PV nodes. So of course, when you're on a PV branch, basically usually is the first move, or like the branch that you're doing full alpha beta window search. So though usually in those branches, you don't want to do early cutoff. Usually in the good branches, you want to full search. You only want to do cutoff when it's not a good move. The second condition is when depth is small enough. So you don't want to cut off at the depth that's very large. So let's say if you cut off at a depth that's very large, usually your search may become worse. Your search may become worse. And remember, our idea is to cut off the branches that do not have potential to raise alpha. But potential to raise alpha in the current nodes means it is greater than equal to, it is basically the value is greater than equal to beta when in the child node, right? So this the full condition to do futility pruning. Okay, so let me do a bit of demo of how futility pruning works. So, okay, so this is my main search routine. So this is just to handle timeout. And then this is my, okay, this evaluate basically is okay. Then this is like basically Poisson search. And then this is the transposition table cutoff. And then, okay, so this is where futility pruning. So I have a static eval. The static evaluation is something that's a combination of the transposition table score with some evaluation. And okay, like basically there's some logic with the static eval. And once I already have the static eval, what I do is if it's not on the main search routine, the main PV branch, then with a certain depth and the static eval. So what I do is I'm gonna comment out the entire futility pruning, and okay, and then let us try to see how much time it takes. Okay, but I think most of the cases I didn't expect that it's going to take that long. Okay, so let's continue to see how much time it takes. So with that, let's just come with like some more techniques to how so far what we've done is basically the techniques to decrease the time, but we haven't exactly increased the strength of our algorithm or like make it more memory efficient, right? So one technique that you can do to increase your memory efficiency is using bitboards. It's basically to take more care of how you do board representation. Okay, so let me just go through some example. Okay, so let's say you want to represent the positions of the position of the pawns. What you might do is maybe you do an array of booleans, right? But a better way to do is basically just use a 64-bit number, right? So the 64-bit number in binary, it is going to look something like this. So we compare the array representation with the just one integer, then obviously the one long integer is better, right? Okay, so let's come to another simpler example. Let's say you want to represent this tic-tac-toe board. One thing that you might think of is just use a 2D array of integers. So it's like 2, 1, by them. 2 is if it's a circle, and then 1 if it's a cross, and 0 if there's none. But a better way to do board representation for this, okay, maybe if integer is too much, right, then you might think of doing using booleans. But instead of using booleans is still using arrays, right? But even better way is just use two integers, basically 9 bits integer. So for example, for x, then you just if the cross is there, then the corresponding bit is 1. If the cross not there, then corresponding bit is 0. And okay, for the same thing for O. So basically you use 2 integers to represent the entire tic-tac-toe board. Okay, so you might be wondering, like, maybe if you use this bit representation, then it might be difficult to do logic with it, right? But the truth is no, not really. So let's say if you want to get the possible actions within this board, what you do is you just do like let's say you just do like x or with O, and then you do an invert of that to get all the possible actions. Right. Then for example, another example is, let's say you want to determine whether in this board whether x is winning or not. So what you do is you determine all the winning lines. So let's say 111 is when X wins the first line, the first horizontal line. And then the second example is when X wins the middle horizontal line. And then you just basically determines all the winning lines. And what you do with this function is you just do X and operator with line equals line. Okay, like basically with most of the things you need to do with that you need to do with the board representation, you can actually do that with bitboards as well. And sometimes it can run even faster than this logic runs faster when you use bitboards than when you actually use like arrays or something. Okay, so let me check if it has successfully done. Okay, like without facility pruning, then you can see that it runs within 28 seconds, so it's not exactly that efficient. Right, so okay, another thing that I want to talk about is board evaluation. So board evaluation is, okay, like sometimes you can, okay, like if you think about how you do board evaluation, right, sometimes maybe you can do like a piece count, like how many pieces are left on the board, or like even account for like positions. But sometimes you can't account for some exceptional cases where maybe you're down by one piece, but your position is very good. Then the evaluation doesn't give you the exact score, right? Sometimes there are a lot of logic that you need to take into account that you can't possibly account for everything. So what you do is, what you can do with this is you can actually use a neural network. Okay, but let me just give you an example of why it is wrong. So like this is an example board, right? So if you count the pieces, so for red you have the two rooks and one horse, one cannon, right? So that's 4 attacking pieces. Then for black you have 2 cannon, 1 horse, and 1 cannon. So in terms of number, it's the equal, but red actually has more rooks than black, right? So in this board, if you use like certain heuristic, then most of the time you will get red having advantage. But if you put this into like the most modern engines right now, then it will say that actually black has a very big advantage. And actually, if you calculate deep enough, like in let's say around 20 moves for black, is actually black can already end the game. So okay, yeah, so there are some exceptional cases that doesn't evaluate very accurately. So what you can do is you can use neural network for this. Essentially, there's a term for this called efficiently updatable neural network. So what this does is you feed the entire board through this neural network, and then the neural network is going to give you the evaluation of the board. Right. So how much time and how many boards that you need to use in order to train this neural network? I'm not connected to internet right now, but if you search on the official repo of Stockfish, they actually use around 10 billion bots and around 7 million training hours in order to train this neural network. So it's not exactly viable when you do it by yourself, but yeah, so that's about it for my presentation. So this is a summary of what I've gone through. Basically, I've gone through like some techniques to enhance your alpha beta pruning, from iterative deepening, where you can use that to order your moves. And then based on that, you can, with the assumption, you can do principal variation search to cut down your search time. Then you need to account for positions where you can't stop the search there. We have to continue because of the capture moves. So that's Poisson search. And then late move reduction is on the assumption that the later moves explored are usually the worst move. So you don't have to explore that deep. So you can cut the depth for that. Then we have transposition table, basically saving the result of your search results previously done. Then futility pruning is to cut off the nodes where it doesn't have potential to raise the value of alpha. And finally, some techniques relating to bitboards and neural networks. So if you're interested to find out, there's this page called Chess Programming Wiki. So there's a lot of techniques. What I have covered is probably only 1/4 of the techniques that 1/4 or 1/3 of the techniques that Stockfish actually use. So if you're interested in find out, you can go to Chess Programming Wiki, or you can even go to the repo of Stockfish. It's actually open source. So yeah, that's the end of my presentation. I'll open the book to all of you.
You said this state-of-the-art model, was it like 7 million hours?
Yes, 7 million training hours.
It's like, how does that work? Like, it's like 7 million single GPU hours.
Yes, 7 million CPU hours. Yes. So it's something like you run your computer for 7 million hours. So it's not done by just one person, but it's actually community contributed. So a lot of people are also interested in Stockfish. Then what they do is they can train the model and upload to this framework called Fish Test. So Fish Test is a framework that helps you make sure that your network and your neural network can work properly. Any other questions? Right. So if no question, I think that's it. Thank you very much.
the big pots, right? Yeah. Yeah, can you send represent? I use like someone.
Yeah, like I actually did this, so like it's basically it's quite a bit of like domain knowledge.